Thank you, Anna, for your introduction. Okay, so I am a researcher in the University of Brescia in Italy, and I am a researcher of National Research Council. The lab where I work is the lab where I work is a sensor laboratory, is a joint laboratory between university and CNR, and we are mainly dealing with metal oxide gas sensor. And where we are in the north part of Italy, near Milan, in between near Milan and Venice. So this is the outline of my talk. I will try to introduce the use of this metal oxide nanowire for gas sensing. So first of all, I will give very brief introduction about the type, the names, the methodological characterization of gas sensor. Then I will introduce material and sensing mechanism, and we'll speak about the nanowires. And then I have a division, something about the preparation of nanowires, only the one we do in our lab, and then something about sensing with nanowires, and I will try to explain what is the convenience in using bundles of nanowires, in using single nanowires, and in using alignment, self-heating, and so on. And I will, at the end, put two examples of the use of heterojunction gas sensor based on nanowires and optical gas sensor. I think that this slide resumes the type of gas sensor you can use. So basically, we have different transduction mechanisms, and among these, we are dealing mainly with resistives, that is the gas interaction with the material produce a variation of the resistance of the samples, and optical. But other techniques are coming on, so I will describe briefly. Mainly, our type of sensor are devoted to investigate the gas species, for example, for air pollution. Air pollution is a huge problem all over the world. Here I reported the detection of atmosphere in the city, in my city, and many parameters are over the level, the accepted levels, and there are type of analyzer which are commonly used by the accepted, but of course many of them are very expensive and bulky, and so the development of miniaturized and portable low-cost gas sensor is of course very important, even if maybe this type of gas sensor, the metal oxide gas sensor, cannot give the same level of detection as the bulky one, but they can be produced in many examples and put in different places around the city to monitor. Okay, so very few introduction about very fast this part. So what one wants from the ideal sensor: high sensitivity, so high sensitivity, high selectivity means that one can say, okay, you have this type of gas and not the other that is present at the same time. For this, someone wants to use the electronic node. High stability, short response and recovery times in order to have very fast detection. The sensor should be robust and durable, low cost, and so on. For gas sensor characterization, one wants usually what we do is a steady state characterization. So we wait that the sensor goes to the stabilization. Sorry, here. So what we want is we do a baseline in the air, then we put the gas and we wait that the sensor reach a stable signal, and then we can have a measure of the parameters that are of interest. And I'm sorry here for the formulas. Okay, so one can get what is the this type of curve. It is the calibration curve, where you have the conductance of the your material as a function of the gas concentration, and you can assign to a variation in the variation of the gas concentration a variation of your output conductance of the material. And often it happens that when you goes up with the concentration, you can find a saturation regime, and the calibration curve usually is not linear, but one has to determine experimentally this calibration curve in order to characterize your sensor. And there are a few parameters that are defined. One is the sensitivity, which is the derivative of the variable that you are observing, that is in our case the resistance or the conductance of the material, over the variable you are investigating, that is the gas concentration. So calculated in a certain point, which is different from the response, what is called the response, which is defining in different way. For example, the variable in gas minus the variable in air divided by variable in gas. But sometimes you can find only the ratio of Y gas over Y zero. So there are other parameters that are important. For example, the repeatability of the measurement. You want that the measurement is always the same, independent of how many measurements you are doing. And you want that the material is stable, that is, the resistance does not vary with time, which often happens. The reproducibility is that you have two identical sensors as the same calibration curve, and the selectivity, which for metal oxide gas sensor is a sort of problem, since they are typically not selective by themselves. So the approach is to try to use different material or different catalyzer on the material in order to have slightly different response to different gases, and to use them into an array of sensors, which is usually called electronic nodes or sensor system, and then use you have an array of signals, and you use a pattern classifier or pattern recognition to get a signal which is more selective than only one sensor. Okay, so for functional characterization, usually we use characterization in a controlled environment using a gas carrier which is air, not nitrogen, since the air is what is more near to the real conditions. So typically we use humid air, we control the humidity, and we detect the resistance or the conductance of the material, and by means of a picometer. So the resistance values is in this range. Maybe more, the better values are between 10 to the 4th and 10 to the 6th to have a readable signal. Okay, so going more to the type of material in metal oxide area, the material usually used since the past are mainly N-type oxides, like tin oxide and zinc oxides, and they cover mostly 90%, more than 90% of the field, while P-type material, which are also interesting for gas sensing application, are covering only less than 10% of the field, even if these materials are very interesting since, for example, nickel oxide or chromium oxide and so on, they have a very good catalytic activity, which is one thing that we are trying to exploit. And the mechanism is staying with polycrystalline material. This technology has been developed at the beginning with polycrystalline material, let's say thick film in the past. And so the mechanism of gas detection is that the oxygen is a ionosorber over the surface when the sample is heated in a region which is, for example, between 250 and 500 degrees C. And when the gas rises, the reducing gases, for example, reacts with the oxygen ionosorb over the surface and creates a reaction product that goes away, and the electron is released back to the conduction band. So if one looks at the conduction band of the material, the band bending at the surface is decreased when the gas arrives. And thus we have an increase in the resistance. So this is the situation is described for N-type metal oxide. For P-type metal oxide, what happens is a little bit different, since with oxygen ionosorb over the surface, we have an accumulation layer, and the gas reaction decreases this accumulation layer. So what we observe with P-type material is exactly the opposite of N-type material, and the problem dealing with P-type material, which are very interesting, is that intrinsically it has been demonstrated. For example, this is the one of the publication where you can find that the sensor response of P-type material is intrinsically the square root of the sensor response of N-type material. So basically the P-type material have lower response with respect to N-type material. Okay, going back to the polycrystalline material, what is the why we want them with nanosize dimension? There is this work, pioneering work of Yamazo, where he demonstrated that if you consider as the diameter of the grain divided by 2 times the Debye length, okay, and in the other scale you have the sensitivity, you increase very much when you go to 2 or 1 times the Debye length, this value. So when the diameter is the diameter of your grain is similar to the Debye length of your material, you will have a switching between a completely depleted material to a conducting material, and you have an effect of detection which is very high. So this was demonstrated for polycrystalline materials, and the problem with polycrystalline materials is the stability of the material. Since this polycrystalline material must be, all materials, metal oxides, must be used at high temperature. So high temperature means that you have grain collations. Grain collations increase the dimension of the grain, and by itself the response of your sensor changes, as well as the initial baseline. So this means that you have sensors that are drifting. Okay, going a little bit on the theory here, it has been demonstrated that if you have a material with diameter A, and the diameter is comparable to the Debye length, okay, the band at the surface are bending like this and are completely depleted. This means that the cylinder is completely depleted of carrier, while if the diameter is higher than the Debye length, you will have band bending at the surface, and in the central region you will have a flat band. Okay. In this case, the effect that you are observing with the gas is only at the surface of your material. And if you now start considering not a grain, so a circular grain, but nanowires, I mean something that has one dimension longer, and the other dimension is characterized by a diameter, which is, for example, compared with the Debye length of the material, you have the same situation as before. That is, if the diameter is bigger than the Debye length, you have the situation of flat band at the center and band bending at the surface. While when they become comparable, you have the situation of completely banded here and completely depleted of carrier situation. Okay. This has been developed for thin film and ultra thin film, but apply also to nanowire. Okay. So for microwire, you will have this type of situation. For nanowire, down to the validity of one model, you will have this type of situation. Let's talk about numbers. For example, for zinc oxide to be in this situation of to be comparable to the Debye length, you have to go 10, 20 nanometers of diameter. So the other are not microwire, but if you go higher, you will have flat band in the center of the nanowire. Okay, so after this, let's say, theoretical introduction, I will show how we prepare. What are the nanowire we can observe, we can use for gas sensing, and the nanowire are something like this, so they can grow on a preferential direction by different type of growth. Now they have been developed by mainly physical and chemical techniques. The type of materials we are considering is zinc oxide, tin oxide, but also other oxide, indium oxide, copper oxide, and so on. And if you reduce the diameter of the nanowires, you can have the onset of quantum effect as well. And generally speaking, going to other application different than gas sensing, you are interested into nanowire materials, but also microwire materials can be interesting. So if you increase the diameter, maybe you can have, for example, waveguiding, but you have to go to microwire, since if you want that light propagates inside the material here, you need that the diameter is large enough. So in our lab, we prepare the nanowires by two methods. Indeed three, but I'm not so expert of the hydrothermal growth. So hydrothermal growth is a chemical method. Two physical methods are used. One is the evaporation condensation method. We can prepare zinc oxide, tin oxide, indium oxide, so mainly N-type material. The method is very simple and cheap, since you just need a furnace, and in the furnace you put the oxide powders or the material powders. For example, for zinc oxide you can have from zinc powder or from zinc oxide powder, and they are heated to high temperature, let's say in the 1000 degrees C, in the center of the oven, and the gas flow, for example, argon gas flow in this direction. And after this, they condense over a substrate, which are put in a different temperature region of the furnace. And in the proper thermodynamic condition, you can have the growth of nanowires. Typically, this type of growth needs the use of catalyzer. Means the growth starts when you have small particles of gold or platinum, are the most commonly used, to start. And this is a bottom-up technique. The catalyst particles is in the liquid phase, and the vapor phase arrives with this material that starts growing with the ball here, and typically you have the catalyst balls at the end of the nanowires. This is the image of the, I think this is indium oxide with the ball at the end of this. But we also observe that you can have the ball at the beginning of the material, like in this SEM image of a forest of nanowires growing upward. And so in this case you have root growth, and the zinc oxide material grows, and its dimension is decided by the dimension of the catalyzer particle, okay? You can have growth of nanowires also without catalyzer, but you have sparse, you have low density, so maybe it's not useful for application. By changing the thermodynamic condition, you can also change the type of material if you have a sort of mesh like spaghetti that are growing, or if you have a lined. And also the substrate where you grow, it makes a lot of difference. So if you change, these were grown on gallium nitride substrate. Usually for gas sensing we use alumina substrate, and typically you have that they are bended like this towards the surface. So they are single crystalline. So what is important is that they are single crystalline. Single crystalline means they cannot grow. Their dimension cannot grow by coalescence, okay? So we have intrinsically stable material, and this is the deposition by thermal oxidation. So we deposit the metallic film, then we thermal oxidize it, and we obtain, we thermal oxidize in an oven, but this time we have just the substrate holder, and we obtain the material. Then for gas sensing measurement, we put a heater on the back, we put platinum, we put platinum interdigitated contacts, and we measure them, and we pack on a TOH package. Okay, let's go to the second part, which is the gas sensing that we can do using nanowires. Typically in the literature you can find conductometric gas sensor. We were one of the pioneering group which asked Wang to use their nanowires. They demonstrated in 2000 to do the gas sensing with the nanowires. Other type of mechanism is the field effect gas sensor. Here is reported work on a single nanowires, and you have that by changing the gate of the FET, you will have a different behavior of the gas sensing. The other one is an optical transduction mechanism. Since many of these materials, like tin oxide and zinc oxide, have photoluminescence properties due to their very good crystallinity, and they have very bright photoluminescence at room temperature. And we discovered that the photoluminescence, this is one of tin dioxide, changes with the introduction of NO2, and goes down and then goes up in a very fast way at room temperature. Another mechanism which is brand new, we investigated the magneto-optic properties by using a new transduction mechanism that involves the magneto-optic effect on this zinc oxide cobalt material, and demonstrated that also this one works at room temperature. And the transduction mechanism of this one, and this one are very different, okay? I will have a poster on this on Monday. Just to let you know that this slide is just to let you know that it's plenty. The literature is plenty of application of this material, mainly zinc oxide and tin oxide, but also other metal oxide are used, molybdenum oxide, tungsten trioxide, all the ones that can grow in the shape of nanowires are being tested for gas sensing application, mainly in the conductometric form, which is the easiest way to do. And among the literature, this is the shape of the nanowire. So this is a line nanowire. So you can see only the top tip of the nanowires. This is sort of these are no more nanowires. These are lamellas made of zinc oxide, and this is tin oxide where you have this sort of spaghetti. But the important thing is these materials comes typically in bundles of nanowires, okay? And they have a dispersion inside. So typically what you have is that you have small nanowires and big nanowires. If you are trying to find a condition where the diameter of the nanowires is comparable to the Debye length, you will have a dispersion. And also the bigger nanowires have higher conduction properties with respect to the smaller nanowires. So the good thing would be to select just one nanowire and to investigate the properties of the one nanowires, okay? So first of all, I will talk about what happens when you characterize bundles of nanowires. This is the easiest feature. Since you simply produce these spaghetti-like nanowires, and you afterwards you leave some space for the contacts, and then you put contacts on top of the nanowires. And basically, what you are investigating is the intergrain connection between the nanowires. Okay, so you are investigating something that is very similar to the polycrystalline material, except for the fact that these one are single crystalline, so they are not prone to the coalitions and or increasing the grain size. But you will have a distribution of size, of course, and so the sensing is based at the nano junction, and the band bending is much near to the case of polycrystalline material. And just to show you a few examples, these are sensing with tungsten trioxide nanowires by thermal oxidation method. We try to prepare them in with two different dimensions, for example, 18 nanometer and 180 nanometer. In principle, they are different since the resistance is much different. Of course, the bigger one have a higher resistance, and we have a variation in the properties. We can have gas sensing with titanium oxide, tubular structure. These were prepared by anodization, is another examples, and these are tubular structures, and of course you can have very nice gas sensing properties of this material. And another from literature is the use of tin dioxide nanorods. They can be, for example, catalyzed with other material, for example, copper oxide or palladium, in order to enhance the response to some gases. So for nanowires apply the same techniques that are used to enhance the sensitivity, the sensor response for the other material, for polycrystalline material, which is decoration with metal oxide nanoparticles or decoration with catalyzer nanoparticles. So for single nanowire gas sensing, so if we want to really understand what is going on the material, you have to select a single nanowire. And when you select a single nanowire, you can really investigate one nanowire, and if you properly select the size of your nanowires, you can have small nanowires and big nanowires, and you can investigate what happens. So Here you have depicted that the gas is depleting, the oxygen ion absorbed over the surface is depleting the nanowires, and when you have the gas, the electrons is released back and you have an increase in the conductance. Okay, so in principle, everyone wants this, but which is the challenge of this technology? You have many challenges. The first one is making contacts. Making contacts involves expensive techniques like FIB and DBL. Focus ion beam, in every case you have that you detach a bunch of nanowires, you disperse in a solvent and put a drop on a substrate. And after this, you deposit the contact, for example, by platinum, by FIB, you deposit platinum or gold stripes over the nanowires you have selected. And you can have contamination in the metal semiconductor junction, but you can prepare suspended wires like in this case. With EBL, you don't have contamination due to gallium ion using the FIB technique, but you cannot prepare suspended nanowires, and the technique, you simply put a drop of the solvent plus nanowires, then you put the PMMA, then you expose the PMMA in the SEM, and then you develop it and do the metallization and lift off. And what you obtain is that you have your nanowires contacted between electrodes. And the problem is that typically the resistance of the contact is not non-transferable. So what you will observe is a curve like this when you do EV, since what you have at the contact is a back-to-back diode behavior. And so with this back-to-back diode behavior, you will have a space charge limited current in nanowires. And so in order to investigate these nanowires, you have to take care about your contact, how you make. The other important thing to say is that if you are trying to use nano-size wires, let's say 10, 20, up to 80 nanometers of this material, I talk about tin dioxide, for example, you will have a very low conductance of your single nanowires, since the material is almost depleted. So in order to measure by a picoammeter, you need to increase the carrier concentration, for example, by illuminating with UV light. Okay, so you will have this intrinsic problem in the characterization. But of course, you can think of using a single nanowires in order to put on also suspended membranes in order to reach very low power consumption on a single nanowire material. And you can also realize an electronic nose by putting different type of nanowires, for example, indium oxide, zinc oxide, tin oxide, and single wall nanotube on different hot plate, and you will have a sort of electronic nose made of a single nanowire material. Of course, the application of this is very difficult. Okay, it's not for developing a sensor which goes on a cell phone, just for demonstration. But another important thing that happens with single nanowires is self-heating. Okay, self-heating means that this type of nanowires are so small that simply by investigating the conductance, you have to put a bias between the two ends of the nanowires, and you drive a current through the nanowires, which heats by Joule effect the nanowires. It has been demonstrated that this type of self-heating is called is high enough to heat up the material. And for example, this is work by Kolmakov demonstrated that if you go from 1 volt to 10 volt, you will have an increase in the sensor response, and the increase in the sensor response is the same that you would have if you heat it. And so you can take advantage of this, which is potentially a problem, since if you give too much power, too much bias to your material, you are going to destroy it. You are going to destroy the single nanowires, which is a problem that we often encounter. For example, you do the EV and you do not carefully check the end state of your AV curve, and you are going to destruct your nanowires. So you can, for example, this is another work, you can demonstrate that you can detect, for example, NO2, and if you increase from 0.1 nanoampere the current to 10 nanoampere, you will have an increase in the heating, in the self-heating, that affects the sensor response in the way to decrease the response times a lot. And so one could think of using this effect in order to reduce power consumption very much, since you don't need to heat. And but this is true for single nanowires. It can be used for bundles of nanowires. Recently, it has been demonstrated that also in randomly ordered nanomaterials, you can have this effect, but this has been demonstrated by Monereo and Prades only with carbon nanofibers, and has not yet been demonstrated with metal oxide. The problem with metal oxide is their conductance. Carbon nanofibers are much more conductive, and so you can have this effect, while for metal oxide nanowires, they are a little bit, I am scared they are a little bit too low, the conductance. Other technique which is interesting is the nanowire alignment. So it is very nice to have single nanowires, but the single nanowire, the individual nanowires, of course, is only one, so can detect a limited number of molecules. So you would like to increase the effect by having many ordered nanowires aligned between two electrodes. So a lot of effort is being done on the is ongoing on the alignment technique. You can use Langmuir-Blodgett technique to align nanowires between electrodes. Of course, you need electrons to be at least to be the distance between electrodes must be less than the length of the nanowires, and the process cover the nanowires with some chemicals, and then they align between them, and then they are collected with the substrate. Other type of alignment, which is more rough, is by contact printing. Contact printing means that you have your forest of nanowires, and then you put on glass substrate some soft material like polydimethylsiloxane, and then you press the glass substrate with PDMS over the zinc oxide material, and you have that the nanowires are oriented in a aligned manner over the substrate. The other type of alignment is the use, investigate the use of dielectrophoresis. The dielectrophoresis simply consists in putting the nanowires in a proper solvent and use the electric field to align between two electrodes. Here are the electrodes and here are the nanowires. This is very much dependent on the type of nanowires you are considering. So, okay. And so, I am now to the last few examples I would like to show, and they are on the use of nanowires with, the first one is on the use of heterostructure chemical sensor, which is very much investigated the use of p-n junction material in order to enhance the sensing properties of the materials, and basically what we did is to prepare zinc oxide nanowires and to cover with nickel oxide polycrystalline material. So in our lab we prepare these zinc oxide nanowires. They are oriented in a mesh-like nanowires. The diameter is 20 nanometer. Then we cover with nickel oxide material by sputtering, and we use two different thickness of nickel oxide. And what we obtain is that the nickel oxide creates columnar structure that are composed of polycrystalline nanowires. And so what happens is that if you only consider zinc oxide, you have this type of response to acetone. If you consider zinc oxide plus nickel oxide polycrystalline nanowire, you will have an increase in the sensor response. This is this one, and a decrease in the response in the recovery times, and the same for the other thickness. But we observe that there is a optimum thickness for this, and this effect is probably due to the interaction of one of the material, which is nickel oxide, with the gas, and while the conduction takes place through the zinc oxide nanowires. The other example I would like to show is on optical gas sensor. The optical gas sensor takes advantage of the photoluminescence at room temperature of the zinc oxide or tin oxide. This is zinc oxide. The photoluminescence is composed of a band in the UV and the defect band. They are very sensitive to the surface termination of the material, so why not to investigate them for gas sensing? This is what we did, and we did in this test chamber, which has a quartz window for access of the optical path, and but is sealed in order to have a gas. So we investigated the photoluminescence. We can also investigate the photoluminescence by micro-Raman system with a Lincoln cell. So we can have a signal which is micro via the microscope. And so we can investigate as well the signal of a single nanowires. And what happens is that our photoluminescence signal is decreased by the introduction with NO2. And if we calculate the area under this whole peak, since we don't have a peak shift observed, we can calculate the area and plot as a function of the gas. And you can see here, if we put NO2 in a humid air condition, and we can have a very nice response at room temperature, which is a very good thing for example, for detection of NO2 in explosive environment. You don't want to heat the sample in explosive environment. And moreover, we can also use a LED source. You don't need a laser to observe photoluminescence. You can observe photoluminescence with LED, since the efficiency of the process is very high. Of course, we have cross-sensitivity to other gases, but it's, the behavior also with time is much different. This is ethanol. And we can think of having this like a portable device, so we can use UV LED to excite photoluminescence, and the photodiode and the filter to detect the signals. Since so we can prepare a portable device. This is just on the sensing principles in the case of photoluminescence. This is for tin dioxide, but the same stands for zinc oxide. And we observe that the quenching ratio, which is the area under the surface over area under the surface in air, follows the Langmuir isotherm, the Langmuir function. And we can also, as a perspective, as I said before, measure the single nanowires Okay, we can select a single nanowires, put mark with the EBL, and detect the PL of this material as a function of the gas. This is what you see from the camera of the microscope. So you need the markers in order to recognize your nanowires, otherwise it's too difficult. So I come to the conclusion and hope that I convince you that with nanowires you can increase the stability of the material. The open question is whether to use individual nanowires or bundles. Of course, depends on your application. If you are more on the demonstration of a principle, maybe you need single nanowires, but if you are on the application, you need low-cost technique in order to have a reliable low-cost gas sensor. And in this case, alignment of the multiple nanowires you can try to align multiple nanowires in order to obtain multiple nanowires gas sensor, which is working. And to increase the sensing properties, you can use, for example, the heterojunction decoration of nanowires, and you can exploit different transducing mechanisms to differentiate the response of the material or to work at room temperature. And this is the picture of my laboratory, and I would like to thank you for your attention, and I am open for questions.